Hello everyone, my name is Hannelore and I'm a PhD candidate at the Physical Chemistry and Polymer Science group, PHYSC, at the VUB. And today I will discuss with you my research on P3HB Go4HB biopolymers, and more specifically how I'm trying to model the crystallization kinetics and study the structure property relations of these polymers. But before introducing the copolymer P3HB Go4HB, I would like to introduce to you the big family of polymers, the polyhydroxyalkanoate PHA biopolymers. Maybe you have already heard about them. I like to describe this family of polymers by the following 4 characteristics. So first of all, the PHA biopolymers are bio-based, which in this case means that they are naturally produced by many microorganisms through, most often through bacterial fermentation. And which is very interesting is that they can be produced starting from renewable carbon sources. Secondly, it's a very versatile family. You can see the general structure of PHA polymers on the slide. But to this day, actually more than 150 different monomers have been discovered. So this versatility in structure of the polymers also leads to a very broad variation of physicochemical properties. Then the third point, they're biodegradable. They can naturally be decomposed by microorganisms, leaving no toxic residues behind. And then fourthly, which is also very interesting, the polymers are biocompatible. They are not harmful to living tissue, which is of course very interesting if you're looking at applications in the biomedical or biotechnological industry. So in conclusion, this family of polymers is very interesting to me and also to various industries because they have this very broad application potential. However, there is still a big lack of commercialization of the PHA polymers. And this is especially true for one of the copolymers, the P3HB Go4HB, which you can see here on the left of the slide. This copolymer is very interesting. It has a superior biocompatibility. The biocompatibility is even better than the other common PHA polymers. And it has very desirable, interesting mechanical properties, which can be tuned by variation of the structure, by variation of the composition of the copolymer. So therefore, it has been envisaged already for some time now to use this material in biomedical applications, for example, using it to build scaffolds for tissue engineering. However, as mentioned, there is this lack of commercialization, this lack of application development. And one of the reasons for this is that there's a lack of in-depth and reproducible structure property relations. And you may wonder if these relations are so important, why haven't they been fully characterized yet? Well, it's complicated to do so because you would need to do a systematic study, but the samples for this study are not just commercially available and they can also not be chemically synthesized yet. So you would need to apply a biosynthesis process. So the entire systematic study really needs this interdisciplinary approach, this collaboration between different research groups, the microbiology, polymer science, organic chemistry, and this collaboration is often lacking. And as you may already guess, this is exactly what I'm trying to do in my research. So the goal of my PhD research is to do a systematic study on P3HB Go4HB biopolymers, and with the end goal of determining the structure property relations. And to do so, I start from the biosynthesis of the samples that I will need. And I want to synthesize samples with varying structural properties, varying composition, varying molecular weight. I continue my research with, of course, characterizing the structure of these polymers, and then studying the thermomechanical properties and also studying the crystallization kinetics of these polymers. The main goal is then to determine the relations, and I will also conclude my PhD research with a case study on nucleating agents, more specifically biocompatible nucleating agents, because the slow crystallization kinetics is one of the slow crystallization rate is one of the limitations of PHA. So to do this study, we really rely on a very nice and very strong collaboration at the VUB between 3 research groups. We collaborate on many topics of PHA research, and the groups you can see on the top right are the microbiology, the organic chemistry research group, and then my group, the physical chemistry and polymer science group. So it's really this interdisciplinary approach and also this strong collaboration that makes this research feasible. My slides, yeah. So I'm now in my second year, at the beginning of my second year of my PhD, which is fairly early. So the focus of my research at this moment is on the biosynthesis of the polymer samples. And to just by using a single culture bacterial fermentation process at a shake flask scale, I'm trying to synthesize samples with varying structural properties, and that's exactly what I want to illustrate to you today. So on this slide, you can see some of my intermediate results that I have acquired so far. And what I want to illustrate on this slide is that just by varying the carbon sources that are being fed to the bacteria for bacterial fermentation, we can influence the biomass growth, the growth of the bacteria. We can influence the synthesis of the PHA, and we can, which is very interesting for me, influence the molar fraction of the 4-HB in the resulting copolymer. In this box, I have a nice example for you. As you can see, these are different carbon sources, and what is the same is the total carbon concentration. It's only the composition of the carbon sources that is being varied. And as you can see, by using single carbon sources, for example, the one in yellow and the one in blue, we have a much lower biomass growth than combining carbon sources together. And this also affects the PHA synthesis. When combining 2 carbon sources, we have a higher biomass growth and a higher PHA synthesis. But what is also affected is then the composition of the samples. Using the yellow carbon source, 1.6 hexanediol, I got almost no PHA. I couldn't even characterize the composition. But still, by adding this carbon source to the medium, we can influence the composition of the resulting polymer sample, and I've already been able to reach compositions going from 4 to 24%. Of course, this is still in progress, but because I would like to cover the entire compositional range. After synthesis of the samples, the thermomechanical characterization follows. And on this slide, I would like to illustrate to you how, just by varying the structure of a copolymer, we can really influence the resulting properties. For example, here you can see a thermogram from DSC analysis, differential scanning calorimetry. And I analyzed a sample of 10 mol% 4-HB and one of 22 mol% 4-HB. And what you can see is that there is a very clear and big reduction in the class transition of the polymer samples. So this really illustrates this tunability of properties that I'm trying to capture in my research. How will I continue my research? Because I'm still in an early phase of my PhD. I will continue, of course, the synthesis of the samples and the characterization. But there are some major challenges that I'm facing in the upcoming months that I just want to mention to you in case anyone would like to discuss these with me. So first challenge is, I have to increase the molar fraction of 4-HB, and I will have to apply other strategies than just varying the carbon sources. Because I'm now limited to 24%. I would like to upscale my fermentation on the shake flask scale, but just upscale it to increase the sample sizes, but this is also not so straightforward. Then to do GCMS analysis, I would need to build a standard curve, which is also something that I would like to discuss. And finally, I will have to do reproducible mechanical analysis of thin film samples. So that was my short presentation on my PhD research. I would like to conclude this with mentioning that we have this very nice and strong collaboration on PHA research at the VUB. I would like to emphasize that we are very open for any type of collaboration, discussion, and of course for expanding our team. yeah, so thank you for listening, and yeah, I hope there are some questions for me.